Hello, my name is Justin Brick, and I'm going to be doing a presentation on my class project, my final capstone report. Me and my group members are doing it on the Yucca Mountain Nuclear Waste Repository case study. The groups consist of me, Justin Brick, and then we also have Eric, David, Kevin, and Tim. My references today for my portion of my report is the Yucca Mountain Project Design Control Process Review Report. This was retrieved online from the NRC website. I got some of my design aspects for my report from there. The next portion is a book that I purchased. It is the Uncertainty Underground Yucca Mountain and the Nation's High-Level Nuclear Waste. I got some of they're basically all the different lab testing that went behind picking the site and the potential problems from the site that could occur. A lot of the different tests, such in that aspect, I got from this book. Other reference was Yucca Mountain Science and Engineering Report. It's from the Department of Energy. It's a massive report, includes many different references. That's where I got a lot of the waste processing and spent nuclear fuel waste processing procedures, as well as some of the graphics in the report today. Alright, so first thing I'm going to do is briefly tell you why we chose this report. We chose it, originally it was the group members, all of us voted on what we wanted to do a report on, and this was essentially what we picked. But more into depth about why we chose this, it was because we wanted to know really what happens with the spent nuclear fuel that most of us have experience with. Most of us have some sort of experience with the Department of Defense, Navy, with the nuclear program, and a lot of us were curious, where's the final resting place of the spent nuclear fuel. Well, this is a potential site where it could eventually go, or would have eventually gone. And we also hope to gain a better understanding of the site's early beginning, why they chose the selection, the nuclear waste processing procedures, any environmental concerns, future plans, and hopefully we're going to be able to dispel any myths surrounding the site. There's a lot of environmentalists that didn't necessarily want this site to go up, so we hope to dispel any myths. So my duties for this report, the background, I'm just going to give you a brief background before I go into my portion of it. But my portion of it is why they picked this site instead of the other proposed, and then I'm going into the design aspect of it, the actual waste processing procedures, waste isolation systems, operational support systems, temperature management within the repository, and then I'm going to conclude it with some questions. I'll leave the floor open to questions. Brief background. There's a Nuclear Waste Policy Act of 1982 that laid out three main assignments, and that was to the Department of Energy, the EPA, and the NRC. The DOE had to basically site, construct, operate, and close a repository for the spent nuclear fuel, while the EPA had to set the public health and safety standards, and while the NRC had to promulgate any regulations governing the construction, operation, and closure of the repository. In 1985, they had narrowed down to three potential sites. That was Hanford, Washington, Smith County, Texas, and Yucca Mountain, Nevada. In 1987, Congress made changes to the act and directed the DOE to solely investigate Yucca Mountain, Nevada, to determine if it was a suitable site for a repository for spent nuclear fuel and high-level radioactive waste. Although they actually started building the site, due to political reasons and loss of funding, the site eventually came to a closure, and they never completed building the site. Alright, so why was this site chosen? Well, they had many different aspects went into it. First thing is how the actual mountain is laid out. So they dug a tunnel for the repository, and from the distance from the top of the tunnel to the top of the mountain, and then from the distance from the bottom of the tunnel to before where the water table is, it's 660 to 1600 feet based on where the mountain is and throughout the repository, the top of the mountain, and then approximately 1,000 feet from the bottom of the repository to the water table. So that's important because for any rainfall that doesn't evaporate and actually seeps through the mountain, it has a long distance to travel before it actually would reach the repository. And then on the flip side, if the radioactive nuclides, when they escape and the waste packages actually fail, how long and how much of a treacherous pass will they have before they actually reach the water table. Also, other things that went into it, the Nuclear Waste Policy Act wanted the site to be able to hold 70,000 metric tons of heavy metal, so the distance into the mountain they could actually dig out, that's a factor that played into it. The characteristics of the rock that would hold the repository, so there's a lot of volcanic tuff, location of the faults, and the last rock being able to absorb the heat generated by the spent nuclear fuel were all factors that contributed to site selection. So here's a basic a graphic so you can get an idea what I was talking about. You have the repository right here. Here's the distance between the surface and the top of the mountain. You can just get a visual representation, as well as you can see from the bottom of the repository to the distance to the water table. Also, it shows you the fault lines that are surrounding it. There's a Ghost Dance fault and the Solitario Canyon fault. This gives you an idea where the fault lines are. The repository falls in between them. It's not actually on a fault line. Next, I'm going to the nuclear waste processing procedures. Essentially, the spent nuclear fuel and the waste, are highly radioactive material that come to the site either via truck or rail system, and they'll show up at the North Portal cash receipt and inspection area. Here they'll inspect it, they'll check for any contamination, and then they'll go to a parking lot where they'll essentially just sit and wait till they're ready to process it, and then they go to a carrier preparation and handling system where they're going to remove any material that were surrounding our casks that were meant for transporting and safety. From there, we're going on to the waste handling building. So try to keep this drawing in mind. I'm going to briefly go over each of these different aspects right now, and then I'll go further slides, go into more detail. But from the carrier preparation building, there's a carrier cask handling system that's going to carry the casks and empty canisters. So from there, it has two different paths. It could go from a canister transfer system, which essentially puts it in disposable containers, the waste, and then it'll go on to be placed within the repository. And then any containers that do not meet the standards or the levels are too high for the spent nuclear fuel, they'll go onto the semi-transfer system, or they'll go into a fuel blending pool where they'll mix the different levels to get the level they actually want. Alright. So now let's go on to each individual picture, or each different station in more details. The carrier cask handling system, essentially the cask, all it does is set it up right and it'll put it on a transfer cart to move on to the next part in its next part in the process. From then I'll go on to the canister transfer system. There's an airlock here. I'll go into more airlocks and ventilations when we cover the operational support system. But from there, go on, it'll have the cask outer lid removed. That's another thing I'll go into later, the construction of the cask. There's an outer lid and there's an inner lid before you get to your spent nuclear fuel assemblies. So they'll remove the lid. There's a purge system that will be purging inside the system and sampling the air. Then your next stop, it will move the inner lid and they'll go ahead and move the fuel assemblies that are in disposable canisters to a disposable container, and which will move on in the process. So, like I said, there's two different avenues that the spent nuclear fuel can go. Next is assembly transfer system. Essentially, same thing. There's an airlock. It'll have the cask lid removed. The cask will get moved to a pool of water. We'll have the lid removed, the inner lid, and then from there the different fuel assemblies are placed in a holding rack. And if you could actually picture this as like a 360 view from here, I don't have it for you, a picture of the fuel blending pool. Essentially, they're getting high and low level spent nuclear waste in their disposable canisters, and they're putting them together to make the actual level that they want. And that's just more of a concern because they care about temperature management of the waste packages. They don't want to put a bunch of highly radioactive material in one and less in another, because we want the waste packages to last as long as possible. Once they're actually mixed to how they want, you come back to right here where they go in an incline transfer cart. We'll move them up to here where they go to a dryer assembly. They'll dry off the fuel assemblies, and then from there we'll go to a disposable container. We'll get the inner lid put on, and it'll move on and catch up to the rest of the process. Alright, so the disposable containers, they'll essentially go to a holding area where the disposable container that has a holding fixture where it will place the inner and outer lids on. They'll place a helium blanket in between the two lids. They'll seal it up, weld it. At this point, this is where it's considered a waste package. You will have these cranes that will lift it and put it horizontally on a transfer cart. And this transfer cart will move on to get placed into the repository. That's generally a real general description of the process. As you can imagine, there's a lot more that goes into the details of removing spent nuclear fuel, prepping it, and then putting it in its container and putting it in a repository. You can imagine all the controls that will go into it. This is just a brief overview. The next thing I'm going to go over is the waste isolation system. So we have the natural and engineered barriers, and they're used to prolong the containment of radionuclides inside the repository and to limit their eventual release. So the natural barriers, that's just talking about the actual rock and mountain itself, which limits the water infiltration. It limits the transport of radionuclides once they actually do escape from their packages. and the volcanic tuff and sedimentary deposits below the water table, which limit the transport of the radionuclides. The engineered barriers, they consist of three different things: the waste packages themselves, the placement, drift, invert, and the drip shields. The waste packages, that's your main engineered barrier. It consists of the container, any surrounding shielding, packing, absorbents. The outside shell is made of alloy 22, while the inner shell is made of stainless steel. Main issue with the waste packages, they're designed, what they're made of. They're only supposed to last approximately 10,000 years. They're supposed to eventually fail. Weak points in the actual waste packages themselves are the welds that actually close the different lids on the waste packages. They try to minimize this by the production and manufacture process of the waste packages. Essentially, after they make it, they let it cool down to 1150 degrees Celsius, and at that point they'll quench in the water, and this puts a compressive stress on it instead of a tensile stress. So that's supposed to minimize the eventual cracking of these welds. The emplacement drift invert consists of the structures and platforms that support the waste package, the rail system, drip shields, and ballast. Ballast is crushed tuff, basically the inside of the mountain that they removed to dig the repository. They're going to put it underneath it and make it essentially granular material. They crunch it up to be granular, and they put it underneath the waste packages. That's supposed to diffuse any radioactive nuclides, make a path that's hard for any radionuclides to escape to travel, and also using the actual mountain material, it's able to absorb the heat generated from the packages. Drip shields, they're corrosion resistant. They divert any liquid or vapor that would form or reach the repository and direct it to the floor. Also, it protects you from any falling rocks. Water diversion surface made up of titanium 7. The structural member is titanium 24, and the feet are alloy 22. The difference in the material for the feet is because there's carbon steel within the repository, and they're worried if titanium and carbon steel touch each other, they'll have hydrogen embrittlement, so they have alloy 22 in between the two to prevent this. Here's an actual cross-sectional view of the emplacement drift and the waste package inside it. So you'll have the drip shield, you'll have the crushed ballast underneath. This is the pallet that the waste package is on, and the structural members. Just gives you an idea of what the waste package looks like and the engineered barriers surrounding it. Let's see, going a little bit more into the engineered barriers. The drip shield, waste packages, engineered barriers are expected to eventually fail. The long-lived radionuclides generated that expect to still be around 10,000 years after the engineered barriers fail will then begin to travel throughout the Yucca Mountain environment. Factors such as groundwater, chemistry, flow paths, rock properties, and behavior of the radionuclides under the conditions expected at the repository all play an important role in determining how and if the radionuclides will move, and once the engineered barrier system fails. So that's some of the people that are against this site, and a lot of the studies gone into it is whether or not once these packages fail, what the radionuclides will do and if they'll escape the repository. Alright, so from here we're going to go into the operational support systems. We have a ventilation system in the waste handling building, and for that we have separate ventilation system, contaminated and uncontaminated systems. So if you're in a contaminated area, your uncontaminated ventilation systems, they'll never meet. And also there's, like I mentioned earlier, there's an airlock, but essentially They use air pressures between the contaminated and uncontaminated areas to prevent contaminated air going into uncontaminated just with like air pressure. And this is just to protect the environment, personnel from any airborne release of radionuclides. Underwater waste handling systems. So this is going to the different pools for the assembly transfer system. You have a water cooling system. Essentially uses a heat exchanger that pumps the pool water through. The heat exchanger is cooled by chill water, and the chill water is cooled by refrigerant. It maintains a water maintains at approximately 60 degrees, and this is to prevent evaporation and algae growth. Next system is the water treatment system. It uses a combination of filters, an ion exchanger bed, and ultraviolet sterilization system. Once again, removing any algae growth in the water, as well as removing any radionuclides in the water, keeping ALARA as low as reasonably achievable. So we just care about the actual levels within the water and within the waste handling building. Next is a supplemental water system. It speaks for itself. It adds deionized water to the pool as needed as water level goes down. Last is a leak detection system. This system has sumps underneath all the pools, and if there's an actual leak, it would actually leak into the sumps underneath, and the sumps would pump the water back into the pool, and it also would set off an alarm to have personnel to carry out actions. Backing up to the water treatment system, it actually pumps all the water from all the pools once completed through every 72 hours. Just something throughout there. Next is the electrical power system. So it's powered from the city, but it has a backup power system that's through a diesel generator and battery system, and it will supply power to all your key safety loads, while on a loss of power, any non-essential loads would actually lose power. And they also have redundant power supply, so anything that has to do with safety of the site, they will actually have a normal backup power supply. And the last thing I'm going over is temperature management. The spent nuclear waste and highly radioactive waste becomes less radioactive in time as radioactive elements decay away. This process releases energy in the form of heat. And the potential to design for the repository of this heat could affect thermal, hydrological, chemical, and mechanical processes and the placement drifts and surrounding rock. So the Department of Defense looked to address these issues in two different ways. One is operate at a higher temperature above the boiling temperature of water, and another one is below the boiling temperature of water. For the higher temperature repository, they thought this would be a good idea because no water would actually reach the waste packages, which would prolong the life and maybe make the packages last longer. But the downside of it is it would affect the properties of the environment. And also, from expected heat release from the waste packages, they would need to ventilation and remove approximately 70% of the heat generated from these packages if we operated at a higher temperature. The lower temperature seems to be the more favorable of the two. Water would get closer to the packages, but still the waste packages, until they actually cool off, would give off heat and still cause evaporation, so the water wouldn't necessarily reach the package much sooner. And also the lower temperatures, they like this because as long as they are able to maintain the site less than 85 degrees Celsius and the humidity under 50%, the Alloy 22 material that the package is made of, and the engineered barriers, they're less likely to corrode. So that's some of the benefits of operating at a lower temperature. At At this time, this concludes my presentation, and I'll leave this open for questions. Feel free to ask if you have any questions. Other than that, thank you for your time.